Welcome to the fourth lecture in this series. So, this is about emerging memory technologies. Well, some have emerged like flash, but the others are still emerging. So, they are mostly non volatile. So, we'll discuss what a non volatile memory technology is. So, what's the main problem with DRAM? The main problem with DRAM is that when you turn off the power, all the data disappears. The next time, so let's say next time you're booting a machine, all the data has to be read from the hard disk. So that makes things slow. And also the other thing is that another problem is you need to do frequent refreshes. That is a problem. If I were to use memory that is non-volatile, in the sense you store it once and it remains there forever, it can also act as a storage device. In fact, it's primarily a storage device. You can use it in place of main memory, but that would not be the best use. At least it's always a good idea to have some main memory and use this to kind of enhance its capacity, kind of work as both like memory and storage at the same time. But otherwise, it is more of a bad idea. And because these should be thought of as storage devices, but faster than much faster than hard disk. And so they're only slightly slower than main memory. So what I can say is that non-volatile memory or NVMs are, let's say, slightly slower. So how slightly? Well, we will see. But they're slightly slower than DRAM memory, but much faster, right? So much faster than hard disks. That's the idea. So for constructing all of these non-volatile memories or NVMs, there is a generic approach. There is a single standard approach that you take for all such memories. And of course, the technology can vary, but as I said, the high level approach is still the same. So you construct a device that has two physical states, two different physical states. You designate one state as a logical 1 and the other as a logical 0. So typically, again, this is a matter of convention. This is not a hard and fast rule that you have two states, high resistance and low resistance. We will see that one is assigned to a logical 0, other to a logical 1 kind of consistently, but as I said, it's not a hard and fast rule. But pretty much the two states of the device electrically would manifest as high resistance and low resistance. We create an array of such devices, same way as we create a DRAM array, exactly the same idea. Then there will be reliability problems, mainly because they are not as durable as DRAM memory, so there are reliability problems. So we use a combined hardware software approach to deal with all of the reliability problems that henceforth arise. So we have different types of non-volatile memories. So we have flash memory. Then we have four more, but let's start with flash. So flash is the typical USB card, the USB drive that all of us use. So here the idea is that you have a transistor with two gates. You have one transistor, you have one gate, and then you have another gate. The other gate is known as the floating gate. So you use a floating gate transistor to store some additional charge in terms of electrons. So based on electron storage or storage or lack of storage, you have two resistance states, right? High and low resistance. And of course, in this case, what happens is that storage of electrons leads to a change in the threshold voltage, which is the most important thing, right? So that's the most important thing. Then we have ferroelectric RAM, where we use a ferroelectric material with a degree of polarization. That is a function of the voltage that you have applied in the past, right? Not necessarily now, but based on the voltages that you have applied, you can change the electrical polarization. Because of that, what would happen is that you would again have a high and low resistance state, and you can store a bit. So essentially the bit, you have two states, so two state means that it is one bit. Magnetoresistive RAM or MRAM. Here again, instead of a ferroelectric material, you use a ferromagnetic material, where the direction of magnetization, so either north south this way or the other way, this is dependent upon the current that was flowing through the device in the past. So then what you can do is you can flip the magnetization. So then it so happens that magnetization in one direction corresponds to the high resistance state, and in the other direction corresponds to the low resistance state. Similarly, phase change memory, which does not rely on either electrical polarization or the direction of magnetization, instead it relies on the fact that you have a device. Its structure can either be amorphous or it can be crystalline. And how is that happening? You basically use a thermal heater. If you kind of heat it up abruptly, then the atoms can't rearrange, so it becomes amorphous. But if it's a slower process, then it sort of comes down to a crystalline state. ReRAM is a similar idea where we have an anode and cathode. And between the anode and cathode, if a conductive filament forms of the material, of course, then basically you have a low resistance state because now there is a path. Otherwise, you have a high resistance. So in this case, a physical path of ions has to be established between the anode and cathode of a device. And the existence of the path means that it's a low resistance path. Otherwise, if there is no path, then it's a high resistance state. So without further ado, let's move to the first kind of technology called flash, which is the most common. Our USB keys use this. So as I said, we have a transistor with two gates, not one but two. So one is called the control gate, which is the original gate, and the gate in the middle is called the floating gate. This is the floating gate. So in the floating gate transistor, which is over here, this determines the character of the device. How does it do that? Well, what you do is that if you apply a very strongly positive voltage over here, then electrons will kind of escape, right? So if electrons escape, they'll get caught in here. Similarly, if the voltage here is negative, you are kind of pushing electrons. But we will see that in the one direction is better than the other. But the main idea is that within this floating gate, we can trap transistors. We can trap electrons. And based on whether charge is trapped or not, we'll have two states. So if the charge is trapped, the state will be a logical 0. If there is no charge trapped, if there are no electrons trapped, the state will be a logical 1. And the crux of all of this is this floating gate over here, which is like an extra gate. So what we will see is that when no charge is trapped, the threshold voltage is what it is supposed to be, which is voltage 1. But when charge is trapped, when electrons are trapped within the floating gate, then the threshold voltage will increase, right? So we will see in a second why. But the threshold voltage will increase. It will become Vt plus, where Vt plus is greater than Vt or Vt is less than Vt plus. We will designate this state as a logical 0. So what happens is that if you look at a typical NMOS transistor, then the gate voltage, the gate to source voltage has to be greater than the threshold voltage for the transistor to conduct. Now what is happening is that if you have electrons here, if we have electrons in the floating layer, what they basically do is that they introduce a negative charge, right? So if let's say this is the gate terminal, this is the source terminal, then what they basically do is that they induce a negative charge. So in the sense, they virtually reduce the gate voltage with respect to the source voltage. So effectively, when charge is trapped, VGS does not remain VGS but it is perceived as VGS minus a voltage delta, because in a sense the gate to source voltage is actually coming down, as I said, because we have electrons. So the effective gate to source voltage is lower. So what happens because of that is that this equation would still hold, but if I were to slightly rearrange the terms, this would be VGS is greater than VTH plus delta. So in a sense, for the transistor to conduct or not be in the cutoff range, the gate to source voltage has to be greater than the threshold voltage plus more, right? So that is why it has to be, so we are referring to this as, in a sense, as Vt plus. So of course Vth and Vt are the same, so slightly abuse the notation here, but Vth and Vt are the same. So effectively what happens is that the gate to source voltage should be greater than a Vt plus. In a sense, it would appear, if charge is trapped, that the threshold voltage is higher, right? Higher than the nominal. That is what it would appear to be. So we will use this fact to essentially create a device that has multiple resistance states, and that's not very hard to find out. So let us say that you apply a gate to source voltage which is kind of between Vt and Vt plus. So what will happen? If the state is 1, it is going to conduct, right? So for this it will be a low resistance state. For the state 0, it will not conduct because it is less than the gate source voltage is less than the threshold voltage, so it will be in the high resistance state. So that is how we can differentiate between the two states of the transistor. So this, I am not using a lot of information here. All I am using is basic first year transistor physics, which is that if the gate to source voltage is slightly higher than the threshold voltage, the nominal threshold voltage Vt, then if the logical state is 1, the transistor will conduct, which means that if no charge is trapped. But if charge is trapped, the transistor will not conduct, it will be in the high resistance state. So the question is that now we know how to operate such a transistor, but how do we write a 0 or 1? So writing a 0, which means basically trapping charge, is known as programming a cell or a device. So what I do is that if this is, if this is my transistor, right? In this case, I have two gates, right? I have small silicon, two silicon dioxide layers. So what I do is I apply a very strong positive potential at the gate. So electrons kind of move up. So as they move up, some of them get trapped in the floating gate and they remain there, right? So this gate, as you can see, is connected to a positive voltage source, so electrons will escape. But all the electrons here, let's say in the floating gate here, will get trapped. So they will remain there. Because they remain there, the cell will remain programmed. So even if I remove the power source, the electrons will still remain in the floating gate. So if this is the floating gate, then the electrons will kind of still remain there. And the next time that I put in the USB key in a separate computer, I can always read the value that is present in the cell. How do I do that? Well, I set the gate to source voltage somewhere between Vt and Vt plus. So then based on whether the cell is conducting current or not, I can make a decision. Writing a 1, which is called erasing, basically would mean do the reverse process, which is kind of extract all the electrons out of the floating gate. So what you do is that instead of a positive potential here, you apply a negative potential which will kind of push the electrons back. So you apply a very strong negative potential. It has to be a strong voltage that will push the electrons back into the substrate, and the cell will again come back to a low resistance state or a logical one, because the electrons that were trapped have been pushed back. So the idea is quite simple, either you pull up or you push back. So this is a basic flash cell which is not very hard. We are setting two threshold voltages pretty much by programming or by erasing. And to read it, all that we have to do is set the gate to source voltage to something between Vt and Vt plus. So there are two configurations. Let's first look at NOR flash. So NOR flash is the way that you would kind of create an array. So in NOR flash, you would kind of pair two cells which are connected to their respective word lines. Because the point is that for every cell, you don't want separate electronics. You kind of want to bunch group them. In this case, there are two. So this is a classic NOR combination. So the first question is why are we calling this a NOR combination? Well, what happens in an OR gate? If any one of the inputs is a 1, the output is driven to 0. So in this case, if any one of these cells is in a low resistance state, then basically the bit line will get discharged like this. So that is why it's called an OR combination. So in general, what we would do is that if you want to read the value in, let's say, cell 1, you would set the word line voltage to 0 here, and we would read the value of cell 1 by setting the reading voltage somewhere between Vt and Vt plus, the word line voltage. I could have a more compact organization called NAND flash, where again I have 8 of these cells or transistors, floating gate transistors one after the other, with an enabling transistor to select this bit line and an enabling transistor between this and ground. So many of these are made for reducing leakage power and increasing the fidelity of the signal on the bit line. But the key point is that to read any one, to let's say I want to read the value of WL6, what I need to do is that I need to ensure that all of these are on a low resistance state, right? So basically all of these are conducting, but some of these could be in a high resistance state, right? So in a sense, I can't ensure that something is in low resistance, but I can always ensure that all of these are conducting. So the gate to source voltage, to be on the safer side, should be greater than Vt plus, so that regardless of the value that they are storing, all of these are conducting. So once all of these are conducting, this becomes a straight wire. This becomes a straight wire. And then what we do is we enable ground select and bitline select. And the voltage on WL6 is between Vt and Vt plus, because that's the reading voltage. So that is how we get to, and then we can of course monitor the voltage on the bit line using our old techniques. So then we will get an idea what is the state of WL6. Is it in a high resistance state or a low resistance state, and consequently what is the value that it stores. So as you can see, even so this design is more compact, no doubt, but it takes more time to read and write, mainly because you will have to enable or disable all of these transistors. So basically not disable but enable. So once you are enabling these transistors, setting VGS greater than Vt plus, then we basically read the value here. So this takes a fair amount of time. So reading and writing hence are much slower than what you would have in a DRAM. So NOR flash, as I said, is very simple, that you enable one of the transistors, and for the other one, what you basically do is that you ensure that nothing flows through it. So you kind of set this to 0, and then you see what's the case. So if it's a logical 1, this will get discharged. So the bit line voltage will be the reverse of a logical 1. If logical 0, the bit line will maintain its voltage. So you just have to flip it. This is not very hard at all. NAND flash is basically, as we have said, a much more compact representation, and for this you will have to ensure that regardless of the value that the rest of the transistors store, the VGS is greater than Vt plus, greater than equal to Vt plus. So here what will happen is that all of these will be conducting, this will be conducting, and this can be read. Of course, what is more common these days is not the single level flash that you are seeing, but it is multi-level flash, where you store multiple bits per cell, not one. So let's say you want to store 3 bits. So you need 8 distinct charge levels. So what you do is that you basically have a more sophisticated device that can store 8 different charge levels. So one of them, of course, would be no charge. But then you would have 7 different densities of electrons in the floating gate transistor. And then you could, of course, have different enabling voltages and figure out what exactly is the concentration of electrons in the floating gate transistor, and based on that figure out the logical value that is stored. So in this case, of course, we need far more fine grained charge storage and a way of exactly detecting how much of charge is stored. So if there are, let's say, 8 distinct concentrations of charge, so there would be 8 different threshold voltages associated with them, VT1, VT2 to VT8. So what essentially a controller needs to do is basically either apply one threshold voltage and based on the amount of current figure out what is the actual threshold voltage, or serially kind of apply one threshold voltage after the other until it finds out exactly what is the threshold voltage of the cell. So this of course takes more time, but if you think about it, we have increased the density of storage substantially, right? So if we are storing n bits in one cell, but of course then we need 2 to the power n distinct charge levels and a way of figuring out what is the charge level at reading time. So of course in this case, in the case of flash, our storage density is high. We are of course much faster than a hard disk because we don't have any mechanical parts. But the price that we pay is the lower endurance. We will see in a second why. So the endurance of these devices are not high. And also the error rate will be high mainly because you're storing some charge, a little bit of charge can leak out. So extensive error correction is required. So ECC codes are required to correct a lot of errors. So given that these are primarily storage devices, they are not really competing with DRAM in terms of speed, but they are definitely better than hard drives, which all of us can attest to. Our phones don't have hard disks, right? They have flash based memory. The reason is this speed. So flash devices, because of the fact that they are storage devices, fundamentally provide access at the level of pages. A page can be somewhere between 512 to 4096 bytes, like half KB to 4 KB. Furthermore, writing is tough mainly because you'll have to apply a very strong negative voltage to push out the electrons from the floating gate transistor. So writing is tough. So what you do is that even though you read at the page level, you kind of write. So writing has to be preceded by erasing. So what you would actually do is that you would kind of deprogram everything and then you would want to write. All right. So basically, if I just go back to the programming slide, which was here, then writing a 0 would be programming, right? And writing a 1 would be erasing. So essentially, in an unwritten state, everything contains ones until you convert 1 to a 0. But the first thing to write would be to kind of erase what is called a block, which comprises 32 to 128 pages. I first erase all of it and then I write. So writing, that is why is tough, and the main reason for this is that we don't want to provide fine grained write drivers for each and every cell. That would add a lot of area and be very complex, right? So our storage densities can't be achieved. So that is why what we do is that we read at a slightly smaller granularity and we write at a much larger granularity, because write would involve erasing data. And so because see, erasing and programming are two different things. Erasing would mean a strong negative voltage, right? Programming then, which is nothing but writing a 0, right? Programming is exactly the same as writing a 0. Would be the same as applying a positive voltage and pulling electrons up. So I've erased the ink. So let's now look at this once again in a different way. So our key argument is that programming or erasing a flash cell, or even reading for that matter, requires some amount of electronic circuitry. And that circuitry is something that takes a fair amount of area, a lot of wires, and you need large voltage drivers. So that is why you don't want to provide access at the level of a byte or several bytes. Instead, you provide page level access. You definitely read at the level of pages. You also write, but there is a little bit of a catch with write, so we'll come at that later. But the first point, which is that you read and write data at the level of pages, is mostly true, but not fully true, because for reads you do that, for writes, as I said, you do something more. What you do is that you group pages into blocks, where a block can contain 32 to 128 pages. You then first erase the entire block, which means convert everything to a logical one. And the reason is, so what is the need? What is the need for erasing? The need for erasing is that once you have written to a page, which means converted it from 1 to a 0, in the sense you have charge there, you can't rewrite it. Rewrite basically means 0 will remain a 0, but for 0 to go to 1, you will essentially have to apply a strong negative voltage and push the electrons back. And that process is known as erasing, which requires a fair amount of circuitry, fair number of thick wires to actually get done. So that's the reason writing again is not possible unless we erase, right? So that is why we read at the level of pages. After erasing, we write at the level of pages. But a page that is once written cannot be written to once again prior to erasing, where the granularity of erasing is much more. It's a block, it's not a page, and it has to do with the fact that erasing requires a high voltage source pretty much, and you would want to do that at a much larger granularity. So now the only question that remains unanswered, which is something that many would ask, is that if you have a lot of writes, what do you do? Right? A lot of writes to, let's say, the same set of addresses. So we have a write, so on and so forth. What do you do? So what you basically need to do is that you need to filter out the writes such that only one write is sent to the underlying device. So what we can do is that every flash device can have a small DRAM based cache which will absorb this entire sequence of writes and convert this entire sequence into a single write. Alright, so the entire sequence will be replaced by a single write. So we will kind of absorb all of them. So this would be sort of like a small write buffer before the flash device. This will ensure that the stream of writes will sort of get more disciplined, in the sense the number of writes will reduce. Then we can do this block based, page based system that I just described. So we thus have a program erase cycle, where a program erase cycle is that you could consider a fresh page that has not been written to after it has been erased. We then write the entire page in one go, which is half to 4 KB. So by default, a cell contains 1. If we want to write a 1, we do nothing. Otherwise, we program it and we convert the 1 to a 0. So back conversion from a 0 to a 1 is not possible without erasing. And erasing, as we have seen, is done at a higher granularity. So that's the reason it is pretty much, if you write once, then you just write, right? So the write remains over there. The erase phase, on the other hand, is when we take a block of pages, not a single page, but a block of pages. This is very important. And we set all of the bits to 1 in the not programmed state, such that we can subsequently write. So that is unfortunately the reality of a flash device, that we have these PE cycles, program erase cycles, where you program and then you erase, then again program, then erase, then program, then erase, so on and so forth. And basically, let's say that finer point here, if let's say we want to write to some part of the block but not all of it, then of course we read it out and we store it in a local DRAM or in some other part of the flash memory, and then we rewrite it. So the question that we have been trying to answer is, how do we write to a page after writing to it once? Well, the first is what I just said, that you copy the full block to a fresh block, right, other than the page that you want to be modified, and the fresh block is something that has been erased. Then you replace its contents with the new contents. So in this case, what you are doing, what every flash device has, is something called an FTL, or a flash translation layer. So it maps logical addresses to physical addresses. So a logical address is the address that the external world perceives. But in this case, what happens is that, let's say a logical address was mapped to one block in flash, and now let's say you want to write to this page in this block. So what you do is that you copy this entire contents of this entire block minus that page to another location, which is fresh, it has just been erased. For this page over here, since you can write at the granularity of pages, you write. Then the flash translation layer, for a given logical address, it was pointing to a physical address which used to be this. At the moment it is not this, but it is this. Alright, so this change has to be made, in the sense the mapping has to be changed from one block to another block in the flash translation layer, and that is how we can effect a write. So as you can see, writing is a complex process where there is a need to move the block, right? So we can either move the block to another place within the flash array, or move it to some location in the DRAM cache, and then pretty much erase, and then rewrite the contents of the block minus the page, and then rewrite the page, write the page with fresh values, and then change the mapping. So this is the PE cycle, and it turns out that the PE cycle is problematic because every flash device can only endure or tolerate a finite number of PE cycles, not a lot. So what happens is that in modern multi-level flash devices, pretty much you are making electrons tunnel through the oxide layers, right? So the voltage gradient is so high that you are kind of pushing electrons, up or down, you are pushing electrons, you are pushing and pulling. So the oxide layer ultimately disintegrates. So that is why only a finite number of PE cycles can be tolerated, which is 50 to 150K. So this basically means that the blocks kind of wear out or age, and the moment they reach this limit, they totally die, right? So that is why we would want the wearing out of blocks to kind of happen equally, right? Equally throughout the flash device, such that no single physical block kind of wears out at a higher rate than others. So what we can do is we maintain a PE counter for each block within flash itself. Then we maintain the flash translation layer, which basically converts between logical addresses, or what we would call virtual flash addresses. So maybe let's also refer to them as virtual. Similar to virtual memory, a mapping table. Then this is mapped to a physical location within flash. The physical location that we have within flash would first be one location, and then the point is, if this is having too many PE cycles, then what we would do is that we would kind of unmap it and map this block to, let's say, some other region, right, which is not having that many PE cycles, such that, as I said, things wear out at the same rate. So which basically means we need to have a precise idea of the counts of all the blocks, how frequently they are being accessed, particularly written to, and how we can sort of distribute them such that physically the wear out level is roughly homogeneous. So we need a mapping table and we need a lot of logic to kind of keep track of accesses as well as predict future addresses. And the process of remapping happens within the flash device. Anytime we buy an USB key, which sort of would look something like this, the entire flash mapping part is happening within the key, so we don't even get to see that, right? And it's all happening inside, including the tables and everything. So what we see is a very well behaved device which presents itself as a storage device as just as an array of bytes. In reality, it is not that way. So in reality, we have a small DRAM cache, or we may have a small DRAM cache. I'm not saying that all devices would have one. Then we would have these tables, of course, to ensure an even wear out. So this is known as wear leveling. What do we achieve with remapping? So wear leveling can be achieved via remapping. Here is how we would do it. So let's say that there is a physical block with a very high PE count. Then we would first copy the contents of this block to another free block, which we will use as sort of a temporary buffer zone. So this copying is easy because all that we have to do is we'll have to read and write, and we assume that the free block is fresh in the sense it has just been erased. So this part can be done. The second option would be to erase the contents of this block. The third is we identify another block which has a low PE count. It's a physical block which has a low PE count. So then what we do is we do a remapping. So we basically, the logical block that this would correspond to is remapped over here, and the advantage of doing that is the next time that we access it, of course we will go here, but the probability of going here is not that high because this has a low PE count. So in a sense we are doing wear leveling, homogenizing the accesses. Now the point is that this has a low PE count, so we should rather focus on increasing it, again to homogenize. So what we do is that we erase the contents here and we copy from the free block to this point. So we are using an additional temporary which is needed, but the swapping of blocks with a low PE count and a high PE count is essential for the sake of wear leveling, right? So wear leveling has to be done in flash to ensure that parts of it don't wear out and ultimately burn out. So this is an essential thing. So this has been done, and this would require some state and, as I said, a remapping table. There is something else that happens which is sort of conceptually similar to wear leveling. It's known as read disturbance. So what happens is that if we read a given cell continuously, so we just keep on reading and reading, then we are essentially setting the voltage to high and then reading. So the neighboring cells, right, in a NAND flash particularly, because of the transition, they start getting programmed, right? So what we do is that we need to enable them. So in NAND flash, the rest of the cells need to be enabled, means the voltage at the gate source voltage has to be greater than VT plus. This is of course not as high as the programming voltage, but this is sufficient to pull a lot of electrons up. So gradually they get accumulated in the floating gate, which causes an issue. Over time, the cell gets programmed, right? Over time that happens. This is known as read disturbance, which basically means that in an array of flash cells, like in NAND flash, the moment we are accessing one cell for reading, the rest are getting kind of subtly programmed like leakage current. This causes a lot of issue in multi-level flash or multi-level, so they are known as MLC flash drives. So it causes a lot of issues there. So MLC stands for a multi-level cell, where, as we discussed, we store multiple voltage levels, not just a binary, but more than binary. This again increases the storage density. So the solution for read disturbance is the same as the solution for a P cycle, for a wear leveling solution, which is that we maintain a read counter at each block. The moment the number of reads, let's say for all the transistors within the block, exceeds a threshold, we do the same. We copy it to a new location and start from a fresh state. So this ensures that whatever little bit of spurious programming that has happened, all of that will all get destroyed, right? All of that will get discarded. So that is why we just move the block to a new physical location and start from there. And needless to say, the mapping table is changed. So now that we have discussed flash, let us quickly move to ferroelectric RAM. We'll not have a lot of slides for the subsequent technologies, but enough to give you a basic idea. So what happens is that whenever we are looking at any kind of metal-like material, you will have slightly separate clusters of positive and negative charge. So a dipole moment would form. And the density of these dipole moment vectors, including their orientation, is known as the polarization. And clearly, this is a function of the externally applied electric field, in the sense that whenever I apply an electric field, then all the negatively charged ions or electrons would move towards the positive terminal and vice versa. So the polarization, in the sense, would align itself to the electric field. Now here is so this is simple physics, but here is the fun part, that there are some materials that exhibit something called the ferroelectric effect. They have, or they seem to have, a memory. So what do they remember? Well, they remember the polarization. So ideally speaking, when the applied electric field is zero, when the external electric field is zero, the positive negative charges should all uniformly distribute themselves. So the sum total of the polarization should be zero, right? Because there is no clear external potential. But that doesn't happen. You tend to see a polarization of a separation of the charges, which is what makes things very interesting, because this is dependent upon the potential that you applied to that material in the past. It seems to remember. So even when the electric field is removed, right, the polarization does not become zero, and that is the memory aspect. So let us look at this somewhat in more detail. So when the applied electric field is zero, there can be two values for the polarization. There can be two logical states, right? So these logical states, as we shall just see, in a sense determine whether the cell has a high resistance or a low resistance. And the polarization, needless to say, is dependent on the history of the applied electric field, as we have just said, because the cell appears to be exhibiting some sort of a memory, some sort of a memory of what was the electric field that was applied to it. So there are a few common ferroelectric materials which show a very high level of remembering the applied electric field and having a polarization even when the electric field is zero. Basically, the voltage across it is zero. The electric field is pretty much voltage divided by the distance. One common such material is PZT. Sorry, just a small quick correction. The electric field, the electric field is proportional to the derivative of the potential, the space derivative of the potential. So basically, if this is the material and the voltage across it is V, and let's say that it's kind of uniformly it degrades, and the separation is D, then the electric field is proportional to V by D. It's actually the negative space derivative, but let's say that the -1, I'm kind of including that in the proportionality sign. It's pretty much the negative space derivative of the potential. And so when the voltage becomes zero, there is no derivative, right? So the electric field becomes zero. So that was a small correction I needed to have over here. Now coming back to PZT, PZT is basically lead zirconate plus lead titanate, right? So it's essentially lead alloys. Shows a fantastic ferroelectric effect. A few more common ferroelectric materials are again barium titanate, strontium barium titanate, right? So SBT is actually a fairly popular material with a fairly strong ferroelectric effect. And sorry, strontium barium tantalate, I'm sorry, I stand corrected. And here again, you can see that, some of these are kind of slightly unconventional materials. But again, the reason we run after tantalum and other rare earth metals is basically because of the fact that they are used in these novel memory devices, and they hold a lot of potential. So the hysteresis curve of FeRAM would look something like this, where the x-axis is the voltage that is applied. And you already know the relationship between voltage and electric field. The electric field is essentially the negative space derivative of the voltage. So what is happening over here is that if we start from, let's say, point A, so this point is when the voltage across the material is negative, it's minus VDD. Then the polarization, the direction of polarization is negative. Then what happens is that the moment the voltage becomes zero, it remembers the polarization to become negative. So this is the memory effect. And negative polarization in this case we say corresponds to logical state 1. And then what happens is, as we increase the voltage, at one point the polarization becomes zero, but it keeps on increasing till we come till point D. Again, when we come till point D, when the voltage is positive, the polarization becomes positive. Now when we reduce the voltage, it takes a different path. It does not come back on the same path. Instead, it takes a different path. From D it goes to E. Again, E is a point of zero voltage. But in this case, the polarization is positive and this corresponds to logical state 0. So E and B are the points where some degree of memory is being shown, where the voltage across the device is 0, but the device is appearing to remember something, namely the polarization, which is just a agglomeration of the dipole moments. And then we come to point F and then to point A, which is the point at which we started. So we can make a full cycle of increasing the voltage, then reducing, and then increasing, right? So this is how you go. So if I want to go from any path B to D, then it's kind of a one-way path. I can't come back unless I go all the way to A and then come back. So this is essentially the path that I follow. All right, where B and D are the memory points. So this is by far the most important graph for a ferroelectric material. So the diagram of a FeRAM memory cell, it's a ferroelectric RAM memory cell, would be very simple, very similar to what we have for a DRAM. We have a word line, we have a bit line, and we have a sense amplifier. So all of these parts are common. What is not common is basically this thing, which is not a normal capacitor but a ferroelectric capacitor, which shows exactly the effect that we saw in the previous slide. So it is connected to the bit line on one side and a plate line on the other side. The reason it is not ground is because voltage has to be both positive as well as negative. So that's the reason you can't have ground, otherwise the voltage will kind of swing in only one direction. So we need a plate line, and basically between the bit line and the plate line, so pretty much if the word line is connected, this becomes the bit line point. Between BL and PL, we need to vary the voltage, and then by varying the voltage, we can set different values of the polarization. Writing to a cell. So writing to a cell is much easier than the read operation, because the read operation is tricky. We'll look at that later. Writing to a cell does not appear to be very hard. So what we do is we set the voltage to minus VDD, then it's going to come to point A, which is a well-defined point for a logical one. right? So for a logical 1, we come here, the moment the voltage is removed, it will automatically transition to point B, and we want it to stay there. If we want a logical 0, automatically we set the voltage to plus VDD. The moment the voltage is removed, automatically the cell will come to point E. It will remain there, right? Pretty much forever, unless of course another voltage is applied, and that would be the logical point 0 for us. So whenever we say that there is a voltage, there are two terminals, right? So this is like a capacitor, one terminal is PL, one terminal is BL. So what do I mean by voltage? Well, the voltage is positive. So voltage is always with respect to the plate line voltage with respect to BL. So if we say that the voltage is whatever, 1 volt, then the voltage of PL is 1 volt more than the voltage of BL. So that is our convention. Now when the cell is disabled, that is the word line is set to 0, the cell would revert to a stable point and remain there, which is what we wanted. All that we have to do is either set our cells to minus VDD or plus VDD. The read operation, on the other hand, is tricky. Okay, is reasonably tricky. So let's look at that in somewhat more detail. Reading from a cell. So in the process of reading, what we do is that we set PL to VDD and the bit line to 0, which means that the voltage is plus VDD. So it will move to point D. But this is easy, right? The point is either it is moving to point D in the B to D direction if it was at a logical 1, or it is moving in the E to D direction. So what will happen is that in both the cases, the magnitude of the current flow will be different. If it is moving from B to D, then what will happen is that the magnitude of the current flow will be much more. So the delta V1, or the change in the bit lines voltage, because it was in state 1, will actually be more, because as you can see there is more movement, right? More movement in terms of voltage. So the current flow will be much more, as opposed to this movement, which will be much lower. So as opposed to the E to D movement. So by the way, we are only showing one movement, but the other movement is, definitely possible. If let's say from E I change the voltage to VDD, it's not going to like come this way. It will just go the reverse way, right here. So the point is, as I said, the arrows are not strictly one way. All right. So of course, at the point D, you have a choice. You can go two ways depending upon how you came. But let's say at point E, if you provide a VDD voltage, it will just take the ED path back, right? This path back. And similarly at point B, if you give a minus VDD voltage, it will just retrace this path and go back. So as I said, not all arrows are one way. But the important point is that if I let's say uh, move to VDD, I have two paths, BD and ED, where one path will clearly consume more current, which would lead to a higher potential increase on the bit line in absolute terms. So delta V1 will be larger than delta V0, which we can clearly see from the diagram also. This can be sensed using the sense amplifiers. But again, there is a problem. The problem is that if let's say we went from E to D, when we remove the charge, it will come back to E, right? So we went this way. If the charge is removed, it will kind of retrace its path. But if we went from B to D, when the charge is removed, it would retrace its path. It will not retrace its path, but it will come back to E, which is not something that we want. So if a cell was storing a logical 1, it will move to cell D, point D, but the moment the potential is removed, instead of coming back to B, it will come back to E, right? Instead of coming back here, it's going to come back here, which is not something that we want. So like DRAM, this is an example of a destructive read, where after reading, you are pretty much destroying the value if a logical 1 is stored there. So that is why after reading, we'll again have to write to restore the value exactly the same as DRAM. So FeRAM versus DRAM. Well, ferroelectric RAM is non-volatile. This part is absolutely correct. There are no refreshes. Absolutely correct. We are very happy. It uses very rare and expensive materials. That is why FeRAM is quite expensive, beyond 64 to 128 KB or half an MB maximum. Anything else will burn your pocket. DRAM on the other side has a much smaller size, very easy to manufacture. It is silicon based, it's very easy, very cheap, right? DRAM has a huge market, now you know why. But as I said, ferroelectric RAM is good for small embedded devices, and there it works quite well. It's very fast also. Destructive reads are an issue, but refreshes are not required, thankfully. Magnetoresistive RAM. So this kind of a memory device, thankfully, does not rely on electric charge, something that we have been seeing. It of course does rely on electric current and the direction of magnetization, which is different. And one good thing is, the moment you don't deal with electric charge, charge doesn't move, so there is less of IR heat loss, less of dissipation. And of course, here we are dealing with magnetization, but changing the magnetization in general does not lead to that much of an expenditure in terms of current. We will see, but these devices have other challenges. But in terms of non-volatile memory, magnetic RAMs, MRAMs, magnetoresistive RAMs, actually, they're not fully magnetic, but magnetoresistive RAMs, because you'll always have a resistive component because some or other current is flowing. They are very, very worthy candidates, but we have unfortunately reached the end of the lecture. So we will discuss MRAMs and particularly STT MRAMs, right? So not just MRAMs, but a certain variety of MRAMs that have a lot of prominence now. We will discuss them in the next lecture, not in this one, in the next one, right? In the fifth lecture of this series, we will discuss magnetoresistive RAMs and look at other few devices, and hopefully conclude with a discussion of the roofline model, which is a good performance model for systems with a large amount of main memory. Main memory, either traditional types or non-volatile type, where it's also doubling up as storage.